G'day beautiful people, Swift here, you're watching Swift Tuition, and in this video I'll be covering real numbers and number sets. So distinguishing between natural, integer, rational, irrational, and real numbers. For more free maths help, use the first link below in the group description to join your Grace free WhatsApp group. I'll be sharing selected resources, updates, and occasional free sessions there. If you want weekly tuition, full worked out solutions, recordings, and the premium group, launch prices are going to be $350 to $450 until the 31st of August, depending on your grade. Prices are going to be doubling on the 1st of September. You'll find both links below. Before we get into specific problems, it does help for us to just cover a couple of key definitions. The first definition I want us to understand is that of natural numbers. So now there's a bit of a debate with regards to whether natural numbers include or do not include zero. I prefer the distinction that natural numbers don't include zero, and whole numbers is all the natural numbers plus zero. But there's no like single global agreement, oh, this is exactly what a natural number is. But I do prefer and feel like convention is better if we understand natural numbers as being numbers that do not include zero, right? So you just want to think about all the counting numbers. So when you're counting, how are you going to count? You're going to count 1, 2, 3, 4, 5. You're not going to say 1.345. You're not going to say 3.1415. You're not going to say square root of 2. You're not going to say square root of 5. 1, 2, 3, 4, so on and so forth. And that's all a natural number is going to be. So these numbers that you've been using since way back when, that is going to be a natural number. The next thing to talk about is an integer. So an integer is really just your natural numbers plus zero, and then the negative version of those natural numbers. So that means I'll put ... just to say that it goes on in the left direction, but we're going to have -3, we're going to have -2, we're going to have -1, we're going to have 0, we're going to have 1, we're going to have 2, we're going to have 3, and we're going to go on this way. In other words, from 0, using 0 as the center, I can go -1, -2, -3, -4, -5, -6, -7 without ending. And same thing from starting with from 0, I can go 0, then 1, 2, 3, 4, 5, and go in the opposite direction and keep on going. Something I didn't really clarify over here is that natural numbers go on and on and on. So there's no limit. If I say not infinity. If I say a million, I can say a million and one. If I say a million and one, I can say a million and two. If I say 1 billion, I can say a billion and one. If I say 1,192,000, I can say 1,192,001. There's always one more that you can add to natural numbers and to integers. So even though natural numbers start only from 1 and keep on going on, there are an infinite number of natural numbers and integers as well, even though they start from 1, go all the way. So they have all the natural numbers, and then they go from 0 and go all the way backwards, right? It's almost like they're bigger than natural numbers in terms of size, in terms of the things that they include. We're still going to say that there's going to be an infinite number of integers. There is a whole field in math where we start to look at the different sizes of infinity and countable infinity and non-countable infinity, but you don't have to worry about that in grade 10. Just know that natural numbers keep on going on from 1 all the way up until as close to infinity as you can get, which you can't, so you just can keep on going on. And integers, same idea, but then starting from 0, going on either side, going from -1 all the way towards negative infinity. Obviously, you'll never reach negative infinity because infinity isn't a number that we can exactly reach, but we are headed in that direction. And then same thing from 0 going from 1 onwards that way. Again, we're never going to reach that particular number, but we know that we are headed in that general direction. All right, now we're going to get a bit more technical when we're talking about a rational number. What is a rational number? Rational numbers are going to be numbers that can be written as P over Q, where P and Q are integers and Q is not equal to 0. Right, what does that mean? This means that we've already established what it means to be an integer, right? So you already have a solid understanding of what an integer is. Now take that particular integer and put it into a fraction. So let's say, for example, I'm going to be talking about a fraction such as 5 over 10, right? Look at this fraction, 5 over 10. Now this obviously can be written as 1 over 2. But you'll notice that the 1 and the 2 are both what? They're both integers. And because the 1 and the 2 are both integers, and I'm able to take some particular number and write it as a fraction where the numerator of the fraction and the denominator of the fraction are both integers, this number is going to be a rational number. Very important. So any number that you can write out where you can write it as a fraction, right, with a numerator and a denominator, and both the numerator number and the denominator number are both integers, then that number is going to be classified as a rational number. Now, that means that I can also, even if like you may not think about it in that sense, think about the number like 2, for example. The number 2 itself is just, right, just a 2, right? If I told you, oh, there's a number 2, you would just write it as 2, like this. But 2 is literally just the same as 2 over 1. So even if 2 does not immediately strike you as a rational number because it does not fit the definition directly, like, or at least as intuitive as you like to think, you're wondering, okay, can this 2 really be written as something over something? The answer is yes, because I can take 2, which is an integer, and divide it by 1, which is another integer, and that's just the same as saying 2. So you'll notice that 2 is still a rational number. Now, you may be noticing something interesting over here, and that is the fact that the number 4, for example, is a natural number, obviously. But you'll also notice that the number 4 is an integer, because you know that integers include all the natural numbers, then have 0, and then also have the negative numbers. So the number 4 is inside of integers, right? But the number 4 can also be, so it is an integer, and the number 4 can also be written as 4 over 1. Because, and we know that 4 over 1 is basically a number that has been written as something over something. In other words, P over Q, and 4 is an integer and 1 is an integer, and the denominator is not equal to 0. So clearly 4 is also going to be a rational number. So what you'll find is that you can find that a single number can exist in multiple worlds at the same time, right? In other words, 4 exists in the natural number world, and inside the natural number world, you're going to have integers. Every single integer is a rational number, right? But not every single rational number is an integer. You got to think about that, right? Because some numbers, such as 3 over 7, are not integers, right? You can't have it looking at it as looking like a nice counting number, be it positive or the negative version of those counting numbers, or even 0. 3 over 7 is 3 over 7. You're done. All right. So it is a rational number because I could write it as P over Q, but P is not an integer and Q is clearly not an integer. Well, I'm lying. 3 is an integer and 7 is an integer, so it obviously is a rational number, but it can't be an integer because it's not nice and whole and full, essentially, right? Like 1, 2, 3, 4, 5, or and then 0, negative 1, negative 2, negative 3, without any fractional bits whatsoever. So you can see that you can have numbers being one thing but not another thing. Now, we just spoke about rational numbers. Now we're going to talk about another world or another field of numbers called irrational numbers. So what is an irrational number? An irrational number is a number that can not be written as P over Q. So we know that a rational number is a number that can be written as P over Q. An irrational number is a number that cannot be written as P over Q. By the way, the distinction we made earlier on for rational numbers where we said the denominator cannot be equal to 0 is because anything divided by 0 is undefined mathematically. So we can't say that it's going to be a number if the denominator isn't, because 0 is an integer, technically speaking, but it's not an allowed integer in terms of rational numbers or just numbers at large, right? But 0 over something is fine. That's fine. It's just the denominator can't be equal to 0. That's just a callback because I realized I forgot to bring that up. But back to irrational numbers. Irrational numbers are going to be real numbers, right? And we'll talk, in fact, I should probably add that. Irrational numbers are real numbers that cannot be written as P over Q. That's important to bear in mind. So what is a real number, right? We'll talk about a real number very shortly. But a real number is just a number that exists, right? It doesn't violate any mathematical laws, such as having the number underneath the square root, obviously, being negative. We know you can't have a square root of a negative number. That does not exist mathematically. I can't say square root of -4, for example. This is not a number that exists in the real world. There is a complex world or a non-real world, but that is outside the scope of the CAPS syllabus, right? As of right now, 2026, I'm filming it. They might add it obviously later on down the line, who knows? But as of right now, it's not part of the CAPS syllabus. So square root of -4, we can't have, right? We can't have 10 of values where 10 is not going to be defined. So you may have not covered it by now, or you may have covered it by now, but an example is 10 of 90 degrees. 10 of 90 degrees is something that does not exist, all right? So we need to understand that, oh, okay, cool. This is not going to be something that's going to be allowed, right, in terms of the real world, right? But we could also have, so that's 10 of 90 degrees. We could also have just the square root of a number, right? So something like the square root of 2. If I gave you something like the square root of 2, you can see that the square root of 2 clearly cannot be written as a over b, where a and b are obviously both integers. Like how else am I going to write square root of 2? Square root of 2, square root of 2. All right, so that's going to be an irrational number. All right, so these are all examples of irrational numbers. You obviously have famous irrational numbers such as pi as well. Pi, you can't write pi as a fraction, right? You may have seen some people do estimations of pi like 22/7, but this is not perfectly pi. Pi obviously has 3.14159265, so on and so forth as its starting digits. If you compare that to 22/7, you'll see that they're not going to actually match up properly. So it is literally physically impossible to try to write pi as a fraction where the numerator and the denominator are both integers, and therefore pi has got to be an irrational number. So we are going to include particularly stuff like surds, right? Stuff like pi, right? So that is something to bear in mind. Now, don't confuse this with something like the square root of 4. Because I just showed you a square root and you think, of course, this is a square root, so that means that this square root number clearly is not going to be a real number. Don't think that that means that any square root is not going to be a real number, right? So I'm lying, not a real number, a rational number. Don't think that every square root is not going to be a rational number, right? Because square root of 4 can be re-simplified, obviously, as just 2, and we know that 2 is 2/1, and this is our p, and this is going to be our q, and it fits the definition where p and q are both elements of integers. In other words, they are both integers, and q is not equal to 0. So please do not obviously confuse that. Something can still be a square root, but require you to simplify a bit further before you can just decidedly classify what type of a number that specific number is going to be. So that is going to be that. And then the final, not the final thing, well, yes, the final thing. The final thing we want to talk about is a real number. So real numbers are basically just all the rational and irrational numbers on the number line. So in other words, every single number that exists that you can actually get from your calculator that you've ever worked with up until this particular point is going to be a real number, right? So in other words, anytime when your calculator did not say maths error when you pressed equals, that is a real number. So square root of 2, pi, Euler's constant, square root of 3, square root of 5, 22/7, 346/297. If it's a number that can possibly exist without violating rules such as the denominator being equal to 0, such as having a negative number underneath the square root sign, if it can exist, then it's going to be classified as a real number. All right, so that is obviously something to just bear in mind. Okay, cool. Bearing that in mind is going to be quite important. Whilst I'm going to cover it in a bit more depth a little bit later on down the line, I do want to speak a little bit about it. Well, by down the line, I mean in a future video. I want to speak a little bit about a decimal and your square roots, right? So what we're going to have is we can have what is known as a terminating decimal. To terminate means to end, right? So a terminating decimal stops something like 0.45, right? 0.45 is classified as a terminating decimal. Why? Because it ends. We can also have a recurring decimal, and that's going to be something like 0.2727272727, and 0.2727272727 is also going to be a recurring decimal. Recurring just means that there are blocks that just keep on repeating. So for example, 0.27, you can see the 27 keeps on repeating. If I had 0.207, 207, 207, that 207 keeps on repeating. Typically, mathematically, we're going to write it as 0.27 with a dash over it, or you'd see 0.27 sometimes and two dots over whatever it is that's going to be recurring. It doesn't mean that every time after decimal points is going to start recurring. So some numbers might do something such as 3.14. I'm not talking about pi. It just happened that that's the first thing that came to mind. But let's say 3.14, and after 14, it just does 323232. So I would write this mathematically as 3.1432 and then do that. So this is going to be a recurring number because of the recurring block that is the 323232 that keeps on repeating itself, right? So that's just something to bear in mind, right? Cool. So that's going to be a recurring number. Okay, so what we're going to do is we're going to then kind of segue into looking at a couple of problems and then figuring out how precisely we're going to classify the different types of numbers in the different categories that do exist for them. Okay, so the first number to have a look at is going to be this one. And in this particular case, we're looking at 8, -5, 0, and 2/3. And the question is to classify each number using all the labels that apply from the list. So is it a natural number? Is it an integer? Is it a rational number? Is it irrational? Or is it real? So those are the things that we want to kind of look at, right? So one thing to obviously notice first is that some numbers belong to more than one set. So for example, every natural number, as I spoke about earlier on, is also an integer, and every integer is rational, and every rational number is going to be a real number as well, right? So that's the first thing to obviously ask yourself, right? So how can I classify the following then? What I can do is I can say that 8 is going to be equal, well, 8 is, I'm using equal very loosely here, obviously, equals typically for an actual equation, but I'm saying 8 is, all right? So 8 is going to be a natural number. 8 is going to be an integer, right? Because remember, 1, 2, 3, 4, 5, 6, 7, 8, and every single natural number is an integer. So obviously 8 is a natural number. 8 is an integer, and then that would obviously make it rational as well, right? And if you're rational, you can't be irrational as well, right? And you can be real as well, right? So every natural number is an integer, every integer is a rational number, and every rational number is going to be real, something to just bear in mind. Then we're going to have -5. Well, -5 does not start from 1, so I'm not going to count it as a natural number, but it does include the negative version of a natural number. And we know that negative versions of natural numbers are going to be integers. But if you're an integer, then you must be a rational number. And if you're a rational number, you must be a real number. And if you're, yeah, that's about it. And then we can have 0, and we know that 0 is an integer, right? Natural numbers just start from 1 and go on from there. But and whole numbers, technically it's also a whole number by some definition. Remember, it's a bit of a definition thing, but it is technically a whole number by most definitions. Whole numbers are typically all the natural numbers plus 0, right? But in this case over here, obviously it is going to be an integer, and it's also going to be a rational number, and it's also going to be a real number. And now obviously we have this 2/3, clearly not an integer, so this must be obviously a rational number because I made it by using integers as a fraction. And if you're a rational number, then you must be also a real number. And that's about it. Okay, so as you bear that in mind, that should be obviously something that makes sense, right? And you can obviously see that 8 can be written as 8/1, and we know that 8/1 is a rational number because it fits the P over Q definition. This can be written as -5/1. This can be written as 0/1, and this can be written as 2/3, which it is 2/3. So we know that obviously that makes a whole lot of sense. Okay, so that's about it. I suggest that you try and pause and try and attempt obviously these questions to see how well you can obviously handle the second part of it. But yeah, it shouldn't be too difficult if you understand obviously how to do the first part, right? So yeah, but anyway, here we've got 14, we've got -9, we've got 0, we've got -3/4. How am I going to handle that? Well, obviously this is going to go and look a little bit like the 14 is going to be a natural number, it's going to be an integer, it's going to be a rational number, and it's going to be a real number. And then we know the -9 is going to be an integer, it's going to be a rational number, it's going to be a real number, and the 0 is going to be an integer, it's going to be rational, it's going to be real, and the -3/4 is going to be a rational number, as it's comprised of a fraction of created by using integers, and then obviously it is also going to be a real number. So that is going to be that. Okay, cool. Hopefully that helps clarify your different stuff. Okay, so now we're going to look at this specific question. It requires you to obviously think a little bit more about obviously what it means for something to be a rational number. So a learner says -12 is not rational because rational numbers are positive fractions. All right. So what should you notice first? The first thing is that rational numbers do not have to be positive. All right. What is the definition of a rational number? Remember, the definition of a rational number is that it is a number that can be written as P over Q, where P and Q are integers and Q is not equal to 0. That's all it means for a number to be a rational number. As long as it fits this definition, it's going to be a rational number. If you think about -12, you'll realize that -12 can be written obviously as -12 over 1. -12 is an integer, 1 is an integer. So -12 has got to be rational. So that is something to bear in mind, right? So the learner is not correct. And then obviously we can classify -12 with the labels that can be attributed to it. And that is the fact that number 2 -12 is an integer, a rational number as well, and a real number, but it is not a natural number. All right, and those are all the labels that can be attributed to -12. And that's about how you'd go about approaching that specific problem. Now, the next problem asks us to decide whether each number is rational or irrational, and we want to give a bit of a definition for something like this, right? Sorry, not a definition, rather a reason for something like this. So these do not look as easy anymore. And in the next, I don't know if it's the next video, but in one of the videos where we speak about recurring numbers, I will be a bit more specific on how we obviously go about looking at stuff like this. But we need to kind of try to understand what it means for a number to be a rational, right? And sometimes rational may not be given to us like directly in our face, but we should still be able to identify it, right? So again, I'll just keep on reiterating the definition. A rational number is going to be a number that can be written as P over Q, number 1, right? As in a fraction, right? So if you're a terminating decimal, if you're a recurring decimal, and if you are a square root, right, of perfect squares being numbers like 1 squared, 2 squared, 3 squared, right? So for example, a square root of 1 squared, right, which is 1. Square root of 2 squared, in other words, square root of 4, right? So square root of 9, square root of 16, right? All of those can obviously be reduced to a nice and cute number. So if I say square root of 16, that is obviously 4, and 4 can be written as 4 over 1, right? Something like root 7, however, is not a perfect square, because root 7, the 7 itself, does not come from some nice natural number squared, right? So 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, all the natural numbers squared did not create 7, which means that root 7 is not a perfect square. And in that specific instance, when it's not a perfect square, but it's underneath the square root sign, we can then classify it as an irrational number. But in other instances, it is going to likely be a rational number. So let's look at 0.45 first and foremost. 0.45 is going to be naturally a rational number, right? Why is it going to be a rational number? It terminates, so it can be written as 45 over 100. That is something to bear in mind, right? Because if you were to take 0.45, right, 0.45 is a decimal, right? And as a decimal, it just basically means it's going to be over 100, right? Well, That's not what it means. But if you think about a decimal, if it's point and the number comes directly afterwards, right? And there's two numbers directly, right? Obviously 100 has two zeros, so we can put that over 100. If it was 0.456, right? That 456, that's three decimals. So that'll be the same as 456 over 1,000. And you can try that on your calculator. Try do 0.45 equals, and you might see if it doesn't give it to you in the correct form directly, you might see in your calculator some particular button that looks a little bit like, S to D or something. It allows you to be able to convert between a decimal to obviously look at the number as a fraction, just to kind of see what happens over there. So that is something to do in case you don't believe me. But 0.45 can be written as 45 over 100. We know that 45 is not. We know that 45 is an integer. We know that 100 is also an integer, and therefore 45 over 100 must be also a rational number. And you can simplify that, but that's not the problem. We just had to obviously figure out if it was going to be a rational number or not. And that's about it. The next thing to look at is 0.27. Now, this is not any ordinary 0.27. The dot 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 implies that it's going to keep on repeating that specific pattern over and over and over again. So that's something to obviously bear in mind. So this is 0.27, 27, 27, so on and so forth, right? What does this mean for us? It's going to be rational. If a number is recurring, we're going to consider it to be a rational number. And in a future video, we'll speak about how we can actually prove that's a rational number. But for now, you're going to have to live on the good old, trust me, bro, right? It is going to be a rational number, but do check out the future video. I think it might be the second video in my algebra series, but I'm not entirely sure. But do check it out to have obviously a bit of a rounder understanding on how that works. And then we're going to have square root of 25. I'll just write it over here as square root 25, but imagine the square root sign obviously over the 25. So what is square root of 25? We know that square root of 25 is going to be, in fact, let me just add a reasoning over here. The reasoning over here would be that it recurs with the block 27, and recurring numbers are rational, right? And then again, we'll learn how to prove how that is going to be the case in the future video. I think it's video 2 of the series, but do not quote me on that. So there's square root of 25. Square root of 25 is going to be rational, and that is because we can obviously say square root of 25 is literally just 5, and 5 is literally 5 over 1, where P is a decimal and 5, which is P, is a decimal, 1, which is Q, is also decimal. And we know that if you create a fraction of a decimal, it's an integer. 5 is an integer and 1 is an integer. Creating a fraction of integers does make your final answer a rational number. So this is going to be rational. Okay, now the exception here, or the outcast, is going to be the root 7, because root 7 can't be simplified any further. It is literally just that, it's root 7, right? If it was root 1, sure. If it was root 4, sure. If it was root 9, sure. Root 16, right? I'm going through 1 square, 2 square, 3 square, so on and so forth, right? If it's any of that, if it's a root of a perfect square, right? A square that came from taking a natural number and squaring that, then yes, it would be a rational number. But this is not a root of a perfect square. So root 1, root 2, root 3, root 5, root 6, root 7, root 8 actually, but we'll get into those categories in, I think that's grade 11 when you talk about surds. But regardless, anything that is not a perfect square, we're going to classify as an irrational number. And if you check your calculator, you will notice that there's no clear recurring block. And that's because it doesn't recur at all, right? It's going to just do, it's going to keep on doing random numbers for eternity, basically, right? So if a number keeps on going on for eternity, but it's not recurring, then it's not going to be a rational number. That's different from a number that is going to go on till eternity, but does recur, like 0.2727272727. That 27 block will never stop, but it doesn't matter. It is still a recurring number, so it is going to be a rational number. Think about 1 over 3. If you do 1 over 3 in your calculator and you press equals and you press the S to D button, right, what's going to happen over here is it's going to say 0.33333333333, and it'll never stop. Obviously, it looks like it stops because your calculator stops, but that number literally never stops going on and on and on and on and on. And even though the number itself doesn't stop, the 3 is a recurring block. It keeps on repeating itself for an infinite amount of times. And because that repetition, we're going to classify that obviously as a rational number, right? Because again, we could have written obviously as 1/3. So that is something to bear in mind when obviously approaching things like this, right? So yeah, that's about it, right? So please do bear in mind that particular core skill. It is going to help you quite considerably with regards to obviously conceptualizing and approaching problems like this. Okay, so that is going to be that. We are going to look at the next problem. So this one is -2.6. We've already looked at something similar. We know that that's going to be rational. So the first one, what have I done? All right, it's going to be a rational number. Okay, so -2.6 is going to be rational because why? It terminates, right? It can be written as -26/10 if you think about it. And -26 is a decimal. It's not a decimal, it's an integer. And 10 is also another integer, and therefore it is going to be a rational number. And then we could also have obviously 0.818181, right? It is recurring. 0.81. All right, I'll just write it like this, right? It is recurring, right? But it's going to be rational still because it recurs. Oof, my handwriting. I could have been a doctor in another lifetime with block 81. Okay, and the next thing is going to be √36. This is going to be obviously a rational number, and the rational number is going to be, okay, so let me say √36 is equal to 6, and we know that 6/1 fits the definition, right? 6 and 6, well, let me try to say, and 6 is equal to 6/1. So that's perfectly fine, right? And yeah, that's about it, right? You can see that clearly that number can be written as P/Q, where P is an integer, 6, and then obviously 1 is another integer. So obviously we've made a fraction out of 2 integers. So that is going to be a rational number. And then we're going to have square root of 10, and square root of 10 is going to be an irrational number. Why? Because 10 is not a perfect square, right? So you would say here that 10 is not a perfect square, and that's the same reasoning that would have also given over here, that 7 is not a perfect square, right? So yeah, that's basically going to be that, and once you can do that, then you're going to be perfectly fine. Okay, so I'm gonna basically, yeah, hopefully that makes sense. Okay, now we also identify the irrational numbers in the list. The final decimal is stated to continue without terminating or recurring. Okay, so this is obviously going to be 5/11. 5/11 is already rational, like it looks cute exactly as it should be. That's P/Q. P is an integer, Q is an integer, no questions over there. Square root of 49 is a perfect square. It's 7. So we know that 7 though can be written as 7/1, and 7 is an integer and 1 is an integer, so 7/1 must be rational. Now square root of 50 is not a perfect square, and because square root of 50 is not a perfect square, also well, because 50 is not a perfect square, square root of 50 can't be a rational number, so square root of 50 is irrational. Now this one wants to trick you because you're looking at 3.1010110. No, it's not. It's 3.10100010001. So you can see there's no repetition block per se. Yes, it looks like it's repeating. You see it's a 1 and a 0, then a 1 and a 0, then a 1 and a 0, but it's not 101010. It is 10 100 10001 100001, and it obviously keeps on going on like that. And because there's no clear repetition, that is also going to be an irrational number because it is stated to be non-terminating and non-recurring, right? So that's basically going to be that. So you can see it says the final decimal is stated to continue, it does not end, and it does not recur. Okay, so that's basically going to be that. All right, so on to the next problem. For each number, give the smallest useful label from this list. All right, what does that mean to be a smallest useful label? Because technically 6 is a real number, but I'm not going to go and call 6 a real number because everyone is a real number over here. So it's not as specific as I would like for this to be. So what we basically do is we use the most, how can I call it? The best definition for this particular thing, right? Like the more specific possible, right? So 6, yes, 6 is a real number, but 6 is also a rational number because it's 6/1. And now 6/1 is also going to 6/1, over 1 is also going to be an integer, right? Because yeah, it's a nice cute 1, 2, 3, 4, 5, 6, right? And then also it must be a natural number, right? Because remember, natural numbers are constant numbers starting from 1. So 6 must also be a natural number. So that's basically going to be that, right? So in this particular case, I can count 6 as a natural number. So 6 can be more specifically referred to as a natural number because that's the smallest useful label for that. So 6 is going to be a natural number, right? Then -4 is clearly going to be an integer. Square root of 8, well, I'm jumping, I'm getting ahead of myself. 11/5 is a clear-cut rational number. Right? Square root of 8, however, you can see that square root of 8 is not a square root of a perfect square, right? Like square root of 9 or square root of 4. So square root of 8, we can say is going to be an irrational number. And then obviously 0.333, right? The dot over here, not the best notation, but it just implies it's going to keep on going on, right? We're going to talk about, obviously, about recurring numbers in the I think it's the second video in the series. But when we cover that, obviously it'll make a bit more sense. But yeah, this is 0.333. It's going to keep on obviously going on with the 3. So we can obviously deduce that this is going to be a rational number because we know that all recurring numbers are going to be rational, right? And I spoke about this earlier on because 0.333 can indeed be written as 1/3 in your calculator, and that literally translates to 0.333. So that is something to bear in mind. Okay, cool. With that in place, then we can move on to this next thing over here. By the way, I will be leaving out a couple of these in future videos. You can download them in the group chat. During the group chat, there should be links to all of these things corresponding to every single lesson for additional practice. Of course, no solutions because that is a premium benefit, but you do get access to at least the practice questions themselves. So there's at least that. Okay, cool. Then we're going to look at this question over here. This 12 is clearly going to be a natural number. And then the -1 is going to be an integer. The 0.125 is going to be a rational number, right? This is 0.125. Remember, there's 3 numbers after the decimal point, which means I can use the the multiple. Oh gosh. Oh gosh, I forget the technical term, but basically I can use I'll use multiple just for this case. I can use a multiple of 10 that basically has, oh gosh, I'm not trying to say a power of 10. I can use a power of 10 that basically has 3 zeros. In other words, I can use 1,000, is what I'm trying to say, because 1,000 have 3 zeros and there's 3 numbers after decimal point. And this is the same as just say 125 over 1,000, right? And that is going to clearly be a rational number. It fits the perfect definition of a rational number. Then we're going to have the square root of 81. Square root of 81 is going to be clearly a natural number. And yeah, that's pretty much it, right? It's a natural number. Why is it a natural number? Because it's equal to 9, right? So yes, square root of 81 is a rational number, right? But more specific, it's a natural number because it's well, let me rather say square root of 81 is equal to 9, which is equal to 9/1. But it's just 9. Well, I should just leave it as 9. No, don't know why I had to go through 9/1. Yes, it's a rational number. Obviously, all natural numbers are rational numbers, but we would be more specific if we say it is going to be a natural number. The next thing to look at is going to be the square root of 3, and obviously square root of 3 has got to be an irrational number. And why is that the case? 3 is not a perfect square, and that is something to just bear in mind, right? And that's basically going to be it. And all five numbers obviously are real numbers. There's no need for us to be more specific than that, but only the square root of 3 is going to be irrational. And yeah, that's about it. Okay. And then we're going to go and look at this and decide whether each statement is true or false and correct any false statement. All right, so we'll read the first one, and that is to say that every rational number is an integer. That is clearly not true. We know that rational numbers can be something like 3/5. 3/5 is not a nice, cute whole number like 1, 2, 3, 4, 5, 6, or 0, -1, -2, -3. Basically, if it has a decimal, there's no way it can be a rational number, right? But we know that some rational numbers can be written as have numbers after the decimal point, right? So that is going to be a big no to the first one. So the first one is going to be false. And we asked to correct any false statements, so we can say some rational numbers are clearly integers, but not every rational number is an integer. And we can give an example. For example, 1 over 2 is rational, but not an integer. And that would be my answer to the first question. Then we can go on to the next question. So for the next question, we're going to say true. And why is this going to be true? That's because every integer is rational, because any integer n can be written as n over 1. I forgot to read the question itself, but okay, the question itself is every integer is rational, and the answer is yes, because if an integer is some value n, I can take that value n and divide it by 1. Even if it's a nice and cute number like 5, 7, 9, I can still say 9 over 1, negative 3 over 1, negative 5 over 1, right? They can all be taken as something over 1. And n, if n already is an integer, right, and I'm dividing it by 1, 1 is also an integer. 1 does not change the original number, but it still matches the definition of a rational number. So every integer is indeed a rational number. Third question is going to be that every irrational number is... The third question says every irrational number is real. The answer is going to be for this one true, right? Right. Rational numbers and irrational numbers together is what forms the world of real numbers. So we'll say every irrational number is real, and I'll just add on to that and say that irrational numbers are real numbers that are not rational, right? They don't have their own real nice and cute definition. As long as you can't write them as a rational number, then it must be a irrational number. The next thing is going to be this one, and that states that a number cannot be both rational and real. That's clearly false. Every rational number is real. Every irrational number is real. So this one is a false statement, and I would say that every rational number is real. So a number can be both rational and real. And that's basically going to be that. So hopefully that has helped you understand everything that you need to understand when it comes to looking at real numbers and classifying them and deciding which is which is which, so on and so forth. That has been Swift, and I'll see you in the next video.